Okay, so this, I'm going to do numbers 20 and 21 together because they are based on the same thing. So here we want to write a nuclear reaction for neutron-induced fission of U-235, and we're given these products. All right, so this is a little bit more complex equation than what we've done before. So we're going to start with uranium-235. Uranium is atomic number 92. Now, this is not going to according to this is not going to spontaneously decay. We are going to actually make it decay by hitting it with a neutron. Now, for our products, it tells us that we have xenon 144. Xenon is atomic number 54. Strontium 90. Strontium is atomic number 38. Okay, and so what we need to confirm here is that we have mass and charge balance. So here on the left we have a total of 236 atomic mass units and 92 protons. So I'm going to subtract here. I'm just going to take 236, or if you really want to say 235 plus 1. Okay, so I just did that, minus 144 minus 90. Okay, so that gives me, I have a difference of 2. And now let me take my 92 protons, 54 and 38. All right, none of them. So my charge is balanced, but I need to come up with 2 more atomic mass units. Well, I don't have a single particle that weighs 2 atomic mass units and has no charge. But what do I do have in my set of tools? I do have a neutron. So what if I said I use 2 neutrons? How about that? So you just put a coefficient in front of that. Okay, this is a trick question, and I'm not a big fan of it because it depends on how you interpret it. This says, how many neutrons are produced in the reaction? My first instinct is to go 2, which I believe is a correct answer. However, to work the rest of this problem correctly, or to save us on some math, notice we used 1 neutron to start this reaction. So there's really only a surplus or a production of 1 more neutron. So you can say 2 versus 1 there. It just depends on your argument. I'm not a fan of this question, so I don't particularly plan on asking you that. But for the purposes of doing part B, I'm going to go with 1 neutron, okay? It's just going to make this math a little bit easier because we got a whole lot of decimals here. So we want to know how much energy is produced per gram. And again, if you are interested at all in nuclear power applications, this is huge for you. Okay, so we're fission here. Okay, so we're going to be calculating mass defect here. So we are starting with 235.043922 AMUs. And then we're going to subtract all of our products here. Now, if you want to use the 2 neutrons here, you need to include the weight of a neutron on this side. So you will still get the correct answer. You just need to make sure you include that here. That's why I'm just saving myself some time and a little bit of math. So let's take our xenon 144, which is really 143.9385 AMUs. Strontium 90, which is really 89.907738 AMUs, and we need 1 neutron, which is not given in the problem, but you can look in the book. It would be given to you otherwise, 1.00866 AMUs. All right, So let's add these up. So this is xenon 144, strontium 90, 1 neutron. Now, if you're going strictly from this equation, you would have 2 neutrons and 1 neutron on this side. It will still work out. Okay, so I'm going to add these up. 143.9385 plus 89.907738 plus 1.00866. And you want all the decimals here, okay? So you write every single one of them down. No, do not round. 43922. I'm just carrying that down. Minus 234.85489. Ooh, gosh, bad writing. 898. Okay, so let's say 235.043922. Subtract that. Okay, so notice there is a difference of 0.189024 AMUs. That is our mass difference, or the mass defect that we're dealing with. We still haven't answered the question because we want energy per gram. This is going to be in joules per gram. And all we have right now are AMUs. All right, so what we need to do first is we need to change our AMUs to kilograms. So yes, it's going to be a tiny number. Okay, so let's take this number, 0.189024 AMUs. Again, don't memorize these conversions. It's not really necessary. So we know that 1 AMU is 1.66054 times 10 to the negative 27 kilograms. All right, so now let's do that. Times 1.66054, 10 to the minus 27. Again, store this. We want to try to keep as many decimals as we can here. So I'm just going to copy. I'm going to round for writing purposes. 3.1388 times 10 to the negative 28 kilograms. Okay. So now, we are going to use our energy from our Newton equation, or Einstein actually, E for Einstein. Energy equals mass, 3.1388 times 10 to the negative 28 kilograms, times the speed of light, which again, we're not using 3, we're going to use our exact speed of light, or more exact, because I told you in 170 that we're rounding it to 3. Here we are not, and we got to square that. Hopefully, if you've had my class already, then you have the speed of light already programmed. If you don't, that's okay. So we're just going to take this number times, I'm going to go ahead and say 2.9979 if you have it programmed, which I should have checked before, but I didn't. Okay. I don't think I did something right. Oh, yeah, I did. Okay. So that gives me, remember, a kilogram meter squared per second squared is also known as a joule. So 2.821 times 10 to the minus 11 joules. And that is how much energy we get from one single atom. You go, that's not very much energy. Yeah, but that's only one atom. So we're going to make this better, because we want joules per gram. Do we have a way to get from grams to atoms, atoms to grams? Hopefully, yes, you remember we do. We know that 6.02 times 10 to 23 of those we call that 1 mole. Okay. So let's do that. And well, here, now let's go ahead and make our conversion. We know that 1 mole, here, let's call this U235. U235. Now, do not look on the periodic table here. Okay, because that's going to give you uranium 238. That's not what the question is asking. This question is asking specifically about uranium 235. So we're going to use this as our molar mass here. And because you know I like 2 decimal places, so I'm just going to round it there. If you want to put all these in, man, go for it. So that's going to give me grams of U235. All right, so look, I'm going to have joules per gram. So let's calculate this. 10 to the 23rd divided by 235.04. So every single gram of this fuel is producing 7.23 times 10 to the 10th joules. So that is a whole lot of energy from not a lot of fuel. We'll leave the discussions about ethics and definitions of clean energy to others, but no one can deny that that this is a very efficient energy production. Okay, so now relating very similar situation. If we convert an entire gram of matter, how much energy are we producing? So we're just going to use E equals mc squared. So here, remember, our mass must be in kilograms. So 1 gram is 0.001 kilograms, or if you want to say 1 times 10 to the negative third. So got to be in kilograms. Speed of light, 2.9979 times 10 to the 8th meters per second, and we got to square it. So 2.9979 times 10 to the 8th squared times 0.001. Or you can say divide by 1,000. So 1 gram of material converted to energy is worth 8.987. If you want to round to 9, that's fine, times 10 to the 13th joules. That is a lot of energy.